All right, how's it going? Welcome back to another video in the series here on group theory. In the last video, we were talking about different types of fundamental groups that we're going to be interested in when working throughout the video series. And if you remember, there are two main types of groups that we were interested in, and that's what I have here on the board. What I'd like to do just to start the video is just to quickly recap what those were so we have those in the back of our mind. The first type of fundamental group that we were looking at was the notion of a cyclic group, right? And the whole idea behind a cyclic group is that it is a group that can be generated by a single element that is typically called the generator. So common notation for a cyclic group is the uppercase letter C, and if there are n elements in the cyclic group, we would say it's C sub n. Another way of describing a cyclic group is we would have a set of brackets, I guess like a left sort of angle and a right sort of angle, and what's in between those is what the generator of the group is. In the case where it is A, then we could say that another way of writing this cyclic group is just a set that has n different elements, where each of the various elements are simply going to be powers of A. Okay, and so that's what a cyclic group was, right? And the whole idea behind the word cyclic is that once we go from the first, second, third, fourth, all the way up to the nth element, if we were to apply another power of A, we would cycle back around to the identity. In other words, this needs to satisfy the property that A to the n equals E, or the identity, right? So that was what we first talked about with cyclic groups, and then we moved on to this other class of groups called dihedral groups. And if we remember, dihedral groups are the set of symmetries of a regular n-sided polygon, or a regular n-gon. And it's denoted by the uppercase letter D sub 2n. And the notation is to describe the number of elements that would be in the group, or describe the order of the group. So specifically, there would be n rotations and then n reflections. And we would denote the letter R to be a rotation and the letter S to be a reflection. And that's kind of what we have with this set right here, right? And kind of the fundamental properties that this group needs to satisfy are, first, is that you can imagine if there are n different rotations for an n-sided polygon, then after we perform n different rotations, we're going to get back to our starting point. We're going to get back to the identity. So this needs to satisfy that R to the n equals the identity. But you can also imagine that if we were to reflect something across an axis and then reflect it back again, I should say this and then reflect it back again, right? It'd be the same thing as getting back to our original starting point. So R to the n equals the identity, but also if we take two reflections, S squared, that is going to equal the identity as well. And then there was one additional property that we briefly mentioned, but we didn't describe too much, but it's still very useful and essential for describing the structure of the dihedral group. And that is that if we want to perform a rotation in the opposite direction, maybe we define R to be a counterclockwise rotation. Then if we wanted to define a clockwise rotation, maybe R inverse. That is defined as the product SRS inverse. Okay. So the cyclic group is denoted by this set of elements that satisfies this property, and the dihedral group is essentially this set of elements that satisfies this property. And what we are going to be doing in this video is just, I guess, taking one additional look at a set of or a way that we can construct fundamental groups. And those oftentimes can involve the cyclic or the dihedral groups. To put it in the big picture of things, what we are doing right now is we're establishing some of the fundamental building blocks of groups that we're going to be interested in. We're going to be looking at many different types of groups throughout this video series. But one of the questions that we can always ask is, well, what is that group isomorphic to? How does that group really behave? And we might find out that, maybe that group, even though it might look very different, fundamentally it behaves just like the cyclic group, or it behaves just like the dihedral group. So that is the big idea in introducing these groups. And for this video, we are going to be introducing just one more I guess, tool that we can use to say that whatever group we're looking at, maybe at the fundamental level, it really just looks like this type of group, okay? And I am purposefully being vague because I would like to introduce this not by simply stating what it is, but I left some room down here on the board to try to motivate this. Now, hopefully, when you have learned about sets at some point, and I know this was mentioned in the video series that we have here on numbers and sets, and I can link this specific video, we talked about the Cartesian product of sets. Because if you remember, we can perform these types of set operations to kind of take in two sets and spit out a third set. Some examples were the union, the intersection. You could talk about the negation of a set, not the elements of a set, right? But one of the things that we could not do with sets is we couldn't multiply two sets. We could multiply numbers, but we couldn't multiply sets. But even though we couldn't multiply sets, there was sort of this construction of an operation that was kind of like multiplication. It's how we could somewhat think of multiplication of sets, even though multiplication of sets is not by itself a thing. And if you remember, that was called the Cartesian product between two sets. And maybe let me just write that out down here. So let's say that I have two sets, A and B. Then I can take their Cartesian product, A cross B, like this. And A cross B is simply going to be, it's going to take in two sets, A and B, and it's going to spit out a third set. That resulting set, that output set, is going to be a list of, or its elements are going to be ordered pairs, A comma B. And the condition on these ordered pairs is that the first element needs to be from the first set in the Cartesian product. So A would need to be an element of the set A. And then the second element would need to be element in this ordered pair would need to come from the second set in the Cartesian product. So A needs to come from A, and then little b needs to come from the set big B, like this. Right? So we developed this notion of the Cartesian product between various sets, and that led to some very interesting sets and very useful sets in many different areas of math, right? This led to the whole notion of Rn in the first place. Because after all, Rn as a set is simply, Rn as a set is simply the set of real numbers in a Cartesian product with itself n different times. It's simply going to be R cross dot 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 cross R, where this is applied n times. Right. So what I'm trying to say is that we developed this notion of a Cartesian product for sets. And also, a lot of times what we have been doing to kind of motivate, if you remember when we talked about homomorphisms, we introduced and motivated homomorphisms through sets. So what we're going to be doing is we're going to be doing a similar idea here, where we're going to take this idea that we've already established with sets and just say, well, if we can take a Cartesian product of sets, can we take a Cartesian product, or the equivalent of a Cartesian product, for groups? And you might be able to tell by the title of this video, that is what this video is going to be about. It's going to be what happens if we try to effectively multiply one group by another. Because it turns out that a lot of the groups that we end up looking at they might end up looking like C something, like Cn cross Cn, Cn times Cm, or something like that. And fundamentally, that is how that group, whatever that group looks like, behaves. It behaves like a type of product of groups. And because a lot of groups behave like products of more fundamental groups, we want to understand what that means to take a product of, or a product, I should say, of groups. So we develop the building blocks and become familiar with them before actually working with them on a more general scale. Okay. So I hope that makes sense. What I'm going to do is to first erase this and write out the definition for what is this product between groups that I'm talking about. So I'm going to erase the board, and then we'll go through that next. All right, so we have the first and really the main definition of this video, the direct product of groups. Let's go through it together. So it says that if we have two groups where the first is G comma, I guess asterisk, and another group H comma dot, then we can define a set, which is just the Cartesian product between G and H, as G cross H. Same way how we define the typical Cartesian product, where the resulting output set is an ordered pair, where the first element comes from the first group, and then the second element, H, comes from the second group. But unlike with just a Cartesian product, where we're just defining a set, a group, as we know, has both a set and a binary operation. So in addition to the Cartesian product being the resulting set from taking a direct product of groups, we need to define this new operation, which I'm going to call times. So if we have two ordered pairs from this set, G cross H, and the first ordered pair is A1 comma A2, and the second is B1 comma B2, then we can define this operation kind of how we'd imagine this operation would be defined, where, and maybe what I should do really quickly as well, just to be absolutely clear, is that both A1 and B1 are elements of G, right? And they have to be. If they're an ordered pair where the first input comes from G, these have to be from G, and then the next two, A2 and B2, have to be elements of H. And I think by explicitly stating that, the operation is going to make sense. If we take this operation times, the way it's going to be defined is that it produces a resulting ordered pair where the first input is just the elements of G acting on each other. And how do elements of G act on each other? Well, through the asterisk operation. So A1 asterisk B1. And then the second element of the ordered pair just takes the elements of the second set, the elements of H, and operates on those according to the group operation defined right here by dot. So we'd have A1 asterisk B1 and then A2 dot B2. And again, because these are two general groups, G and H, they don't need to have the same binary operation. So that's why we're being very, very precise here when differentiating this with this with this. This is the operation from the first group, this is the operation from the second group, and the times is the binary operation associated with this resulting group, G cross H. So maybe just to be, and maybe I shouldn't even put times, let me put circle actually. So, and we'll see why in a second. Maybe circle is the operation. So that way, the idea is when we take a direct product of groups, the set would be the Cartesian product G cross H, and the corresponding binary operation would be this little circle that we have right here. Okay. Hopefully that makes sense. Now we might have the question, why do we want to do this besides the fact that we can do this? And the first answer is, well, we can do it. So, but we might want some more motivation. When would we do this? It might be a better way of asking that question. And the idea hopefully will make sense from this example that I'm about to give. This is just one example, but I think you can see the generality when we provide it. For example, when we were talking about the group D2N, that is the symmetries of an n-sided polygon. So, and when we were talking about this, I think in the last video, the specific three-sided polygon, okay, the triangle, this would be D sub 2 times 3, or D sub 6. So D sub 6 was the symmetry to describe a regular triangle. I'll try my best to draw a regular triangle. But let's say that the system that we are working with does not just contain a single polygon. Let's say that this system that we're working with has two polygons with it. Where maybe the first one is a triangle, and maybe we also have a square or a regular four-sided polygon. And maybe we want to ask, what are the symmetries of this combined system? Not just the triangle by itself, which we already know is described by D6, and not just the square by itself, which we already know is described by D8. But what are the symmetries of the triangle and the square together? And the answer to that is, well, for every symmetry of the triangle, whether we rotate it or reflect it, we can always just leave the square the same. We could leave it untouched. And vice versa, we could perform any manipulation that we want on the square while leaving the triangle unchanged. So the idea is that because these are independent objects, the group of symmetries is going to be the group of all the symmetries of this one paired up with all the symmetries of this one. In other words, all possible ordered pairs, as long as the first element of the ordered pair comes from here and the second element of the ordered pair comes from here. So we would say that the symmetries of the group of the triangle and the square in combination would simply be this resulting direct product, d6 cross d8. So let's write that out. That'd be d6 cross d8. And the elements of this group would behave fundamentally like this group right here. And you can imagine too, this allows us to generalize to any number of not just polygons, but just any type of group that we want. If we want to combine many groups together, this is the way that we can do that, through this notion of a direct product. Okay. Hopefully that idea makes sense and why this can be useful. It helps us build more complicated systems out of simpler components. All right. Now, what I'd like to do is say, okay, well, we introduced this notion of a direct product, and what we would like to do is to start just establishing some statements. The first is I think going to be a kind of a fun one, because it's going to be our first instance of showing that two groups explicitly are isomorphic to each other. We're going to be doing a lot of that in this video series, and it's going to be useful to just get started with that process, learning how to show that two groups are isomorphic. So I'm going to erase the board, and then we're going to go through that proposition next. Okay, so we have our first claim involving an isomorphism between two groups. So excited to get into this. And this is the statement right here. It says that the direct product between two cyclic groups, Cn cross Cm, is isomorphic to the singular cyclic group, C sub Nm, if and only if the highest common factor between N and M is equal to 1. Okay, and just to make sure that we're familiar with this too, this is some notation from number theory, where another way of denoting this is just maybe to say the highest common or the greatest common factor between N and M. So essentially, if N and M are co-prime numbers, then this condition must be true and vice versa. Okay. So this is an if and only if statement, which means that we need to prove it both ways. And I'm going to start by proving it backwards, just because that's going to be a bit shorter. I want to do the shorter one first. So maybe let me just write this out. So if N and M, their greatest common factor is 1, then we know that C sub N cross C sub M is isomorphic to C sub NM. And just before we really dive into the proof, what I want to do is just to tell you a kind of a general strategy that we can use, or a general way of thinking about showing how two groups might be isomorphic to each other. And I want to go back to the analogy of two different chessboards. And let's suppose for a second, maybe I'm going on a little bit of a tangent here, but let's suppose that I have one chessboard, maybe just even draw a pretend board, and I have another chessboard over here. And they have their pieces on the board, and I want to determine if this game of chess is really the same as this game of chess right here. And of course you could say, well, you could just move the pieces according to the rules of chess, and then they're the same. But let me also suppose that this has a set of rules. Maybe I'll call them rules 1 here and rules 2 for this board right here. And the first set of rules tells us how the pieces on this board interact. And then the second set of rules tells us how the pieces on this board interact. And maybe what we want to do is to say that if these rules belong to this board, and if these rules belong to this board, then are these really are these boards the same game? Are they both chess? And I would ask, how would we go about determining that? And this isn't meant to be a trick question too. You can probably imagine, well, let me read the first set of rules and say, okay, this is how the pieces on this board interact. And let me read the second set of rules, see how the pieces on this board interact. And if the pieces of the chessboards interact in the same way, we can say, yes, they are the same game. We are playing the same game between these two boards. But maybe let's say that the pieces on this board interact differently than the pieces on this board. Maybe on this first board, pieces act how they normally would, according to the standard rules of chess. Like a pawn can only move up one after its initial move, right? But maybe on this second chessboard, maybe pawns can move literally anywhere. They're not restricted by any type of movement or by any amount of spaces. Then what we would say is, because the pawns, the elements of this board, interact differently than the elements of this board, therefore we are not playing the same game of chess. These are not fundamentally the same. Okay? And the same idea applies to groups. What we can do to determine if two groups are isomorphic or algebraically the same is by looking at the elements of this group and this group, seeing if the elements of these two groups interact in the exact same way, or if they interact differently. So that's going to be a general strategy that you'll see throughout the video series and throughout the various problem sets. Okay, but that's enough talking. Let's actually get to proving this, right? To start, I want to just introduce some notation. Let's say we know if we have a cyclic group, then it's generated by a single element. That's what it means to be a cyclic group, right? So let's say C sub n is generated by the element A, and maybe C sub m is generated by the element B. So, okay. Well, then we know that if we were to take the direct product between Cn and Cm, so just writing it out, Cn cross Cm, that would be fundamentally generated by the first generator, or the ordered pair, where the first element is the generator of the first, and the second element is the generator of the second. It's generated by this ordered pair right here. Okay. And let's also introduce some additional notation. Let's remind ourselves what the order of a group essentially means, or what it means to have the order of a group. And the order of a group describes the number of elements that are associated with a group. And the order of the group is related to the order of an element of a group, right? And if you remember in the last video, we showed that the order of this group right here, or in other words, the order of Cn cross Cm, that is the same thing as the order of the specific element. That is the order of the element which generates this cyclic group. This is kind of the main proposition that we proved in the last video. And let's just give this thing a name. Let's call this K. We can call it whatever we want, but let's just give it a letter, K. And let's make sure we understand what that means. If the order of this, what am I trying not to say this? If the order of this ordered pair, if the order of this pair is K, what that tells us is that within this group Cn cross Cm, that K is the smallest power that we could raise A comma B to in order to get back to the identity element. Okay, and let's write that out. What this is saying, that the order of this ordered pair here is K, that tells us that if we take our ordered pair element, raise it to the K power, then we are going to get the identity element from this group. And even though we didn't mention it in the last whiteboard, hopefully it makes sense what the order, or what the identity element of this group is going to be. If this group has an identity element, maybe I'll call it E sub n, and this group has an identity element E sub m, then the identity element of the direct product of these two groups is just going to be the ordered pair E sub n comma E sub m. And when we say that the order of this element is K, what we're saying is that K is the smallest number that we can raise this power to, such that this equation is true. So all of this stuff, we know that structurally all this stuff must exist from previous videos. We're just establishing some notation to describe some of these concepts that we've been talking about. Okay. So hopefully this makes sense so far. We haven't said a whole lot, just introducing notation. Let's keep going though. Let's make sure we understand what this means. If a comma b is raised to the k, hopefully we remember how the binary operation for the direct product is defined. Another way of saying this is that we can apply let me just write this out. A comma b to the k is just a comma b times a comma b times times a comma b k different times. And the way that this interacts is that a multiplies a by the operation defined within this group, and b multiplies b by the operation defined within this group right here. So if we were to take this direct product k different times, what this is just going to equal is a raised to k different times, and then b raised to k different times. And if the order of this element is k, that should equal this right-hand side. So a to the k comma b to the k should just equal the identity element from the first and the identity element from the second. Okay? Hopefully this step makes sense. And again, pause the video if steps are confusing. I do hope that I'm being thorough, but if I'm going too quickly, that's the nice part about having a video, right? Is that we are able to pause it. Okay. Now, if we know that a to the k is equal to the identity and b to the k equals the identity, we can make some additional statements. All right. And to remind ourselves about what these statements are, let's remind ourselves about how these groups are kind of defined right here. C sub n, if it's generated by a, then another way of writing C sub n, and I'll write it maybe over here, is the identity element a squared, all the way through a to the n minus 1. All the way through a to the n minus 1. And this group has the property that if we take a, raise it to the nth power, it's going to equal the identity. That's what it means to be a cyclic group. That's how its elements behave in this group. Same thing with b, but just slightly different notation. C sub m is going to have the property that it has its own identity element, e sub m, and then b squared, all the way through b to the m minus 1. And it has the property that if we take b to the m, it's going to equal its identity element. Okay? So if we know this has to be true and we know that this has to be true, then inherently we see that raise it to the n, we get the identity, raise it to the m, we get to the identity. We also see now that we're raising it to some new number k, the order of this generator. If we raise the ordered pair to the k, we also get the identity. The only way that can be true is if k is some multiple of both n and m. Right? Because if we have any multiple of n, this will be true, and any multiple of m, this will be true. So because of those statements right there, that implies that n divides k, or in other words, k is an integer multiple of n, and k is an integer multiple of, k is an integer multiple of m, or m divides k. Right? Hopefully that makes sense. Now, if that still makes sense, let's just keep going. So we know that k needs to divide both n and m. And what we started with our initial assumption, we haven't said too much yet about the initial assumption. But if the greatest common factor between n and m is 1, and additionally, k is the order of this element, where, again, let's just remind ourselves what the order of an element is. The order of an element is the smallest power that I could raise this to that gets me back to the identity. So because it's the smallest power, and the fact that their greatest common factor is 1, Another way of saying both of those conditions together is that k is the smallest number that divides both n and divides m. And we'd ask ourselves, what is the smallest number that divides both n and divides both m if their greatest common factor is 1? And we learn from number theory that if two numbers are co-prime, if two numbers are co-prime, the smallest number that each of these divides is their least common multiple, which is simply the product n times m. I hope that me stumbling a little bit there didn't make that confusing. Let me say that one more time. Because the greatest common factor between them is 1, and k is an integer multiple of both, the smallest integer multiple of both of these is simply going to be their product, n times m. So, because of this ends up telling us that k is going to be the least common multiple between n and m. And in the case where they are co-prime, that is simply their product, n times m. All right. So hopefully this makes sense. Right, yeah. So and now we're essentially done at this point with proving the statement one way, because if the order of this element a comma b was k, that tells us that the order of that group is going to be k. Let's see why, in case that is confusing, because I know there's a lot going on, right? The order of the group C sub n, or rather the order of A, the order of the element A in the group C sub n is n, right? The order of the generator is the number of elements in the cyclic group. A to the n equals the identity. Same thing here, the order of this element B is going to be m, because b to the m equals the identity. So by that same logic, the order of this ordered pair is going to be the number of elements in C sub n cross C sub m, which is k. So another way of saying this is that the order of a comma b is nm, and because it is a cyclic group, this therefore has to be the group of this order, the cyclic group of this order. This has to be the group C sub nm. Therefore, we've just shown that C sub n cross C sub m is isomorphic to C and m. A lot of pieces going on, right? But what I'd recommend is even if there are a lot of pieces, pause after each piece and make sure that each piece makes sense. And I think if we break things down, just going step by step, that will really help us understand what's going on. And I hope I'm not going too slow or too fast. But this is all just proving the statement one way. We got to go the other way still. Only halfway done. So what I'm going to do, because we're out of room, I'm going to erase the board, and then we're just going to prove the statement the other way. Okay, let's prove the statement the other way now. And what we're going to do to do this is we're going to actually prove the contrapositive statement. And maybe I should just write that out so we have that. Let's start by assuming that n comma m, their highest common factor, is not equal to 1. And then we want to show that implies that Cn cross Cm, Cn cross Cm is not isomorphic to the cyclic group Cnm, okay? And the way we can do this is I want to start by using a result that we have from number theory, where let's remind ourselves of this, that the greatest common factor, highest common factor between n and m, if we were to take this, multiply it by the least common multiple between n and m, that necessarily needs to equal the product n times m. And let's say that I was going to just isolate for the least common multiple. I just divide the greatest common factor over to the other side. So I would have that the least common multiple of n and m is this numerator, n times m, divided by their greatest common factor. And if you remember in the last whiteboard, we said that this least common multiple, that's what we called k. That was the order of the element a comma b. Maybe I shouldn't have erased that. But we said that a comma b raised to the k was the same as a to the k, b to the k, which was the identity element in this group right here, right? The Cn cross Cm group. Now, what we're going to start by assuming is that the greatest common factor, and let me just be consistent, write that. The greatest common factor between n and m is no longer 1. And if the highest common factor between two numbers is not equal to 1, then it has to equal some number that's larger than 1. And what does that tell us? That tells us that now within this equation, that is always going to be true for any two integers n and m, that if the denominator here is larger than 1, the corresponding least common multiple right here is going to be n times m divided by something larger than 1. In other words, the least common multiple is inherently less than n times m. And that's going to be important, because if k is the least common multiple, and if the denominator is no longer 1, that provides the condition that the least common multiple, k, needs to be strictly less than the product n times m. All right? Say, okay, but let's continue to put the pieces together. What this is telling us is that if we have any element from this direct product right here, and let me just write out, this is an element, a comma b, from the direct product. So if we have an element a comma b, that is an element of the direct product Cn cross Cm, and it satisfies this equation right here. In other words, it satisfies that a to the k equals e sub n, the identity from here, and b to the k also equals the identity from c sub m. We know that these have to be true. All right, that's kind of what we established right here. What we have also just established is that k is less than n times m. And that's going to be important, because what that tells us is that whatever this element is, a comma b, that inherently, if k is less than n times m, then the order of this element right here must be strictly less than n times m. For any element, this is true regardless of whatever element we pick. Why is that true? Because when we raise it to the k, we have to get the identity, and k is less than this. Maybe let me even write this out in words. So any element in this direct product Cn cross Cm has order less than n times m. Because it's guaranteed to have an order k or smaller, and k by itself is less than n times m, right? I might be saying, okay, how does this get to showing that this is true though? And this is where we want to be looking, again, to show two groups are isomorphic, we want to look at the elements of a group. Let's look at the elements of this group C sub nm. We know that, we showed in the last one that these two are isomorphic, but just in general, if C sub nm is generated by some element, we can call it whatever we want. Let's call it R, I don't know. It's a cyclic group, so it's generated by some element. And if we were to write this out in set notation, this would be E, R squared, all the way through R to the nm minus 1. In other words, this cyclic group C sub nm needs to have the property that the order of R is equal to n times m. Okay? Because R raised to the n times m should cycle back to the identity. Now this is where we can put the pieces together. Because if C sub nm has an element that has order n times m, one of its elements has this order. And we're saying that in this group, Cn cross Cm, that any element in this group has to have an order less than that. there's no way they can be the same group. There's no way that every element of this group has an order less than n times m, and that an element of this group has an order of, does have an element of order n times m. So because the elements in this group and the elements in this group have different orders, therefore they cannot be isomorphic, and therefore Cn cross Cm there is not isomorphic to Cnm. Right? That proves the statement the other way around. Again, I hope that this makes sense. Yeah, I'll leave it at that. But this is, it might feel a little bit dense at first. I will say too, as we go through more of these, hopefully it will get a little more familiar, that we can show groups are isomorphic or are not isomorphic by looking at the elements of the group, looking at their orders. How do the elements interact? How many times do we need to multiply an element before looping back to the identity? Okay. What I want to do now, just to finish off the video, because I feel like this has already gone on long enough, is there is a general theorem that is incredibly nice, and it is conveniently called the direct product theorem. And what we have shown right here is that this group, the cyclic group C sub nm, is isomorphic to the direct product Cn cross Cm. But it turns out there's a general criteria that we can use to show that any group is to determine whether or not a group is isomorphic to a direct product of two potentially simpler groups to work with. So let's write out that theorem and then we'll go through that next. Okay, so we are on to the direct product theorem to finish out the video. Let's see what it says. It says, let's suppose that we have a group G and we have two subgroups H1 and H2. They're both subgroups of G. And let's suppose that these three conditions that right over here, these three conditions are true. We'll go through them, but if these three conditions are true, then we know that the group G is going to be isomorphic to the direct product of its two corresponding subgroups. And what we really did in the last couple whiteboards was just prove a specific version of this more general case. But what are the three conditions that need to be satisfied? Well, the first is that the intersection, because these are inherently sets, the intersection between H1 and H2, between the two subgroups, is only the identity. So the only element that both of these subgroups have in common is the identity element from G. And notice too that we're not distinguishing an identity in this one and an identity in this one. They're both subgroups of the same group. So the group G has an identity element, and that has to be the same identity element that belongs to both H1 and H2. So we only have one E in this theorem. Then for the second criteria, we're saying that whatever element we have in the first subgroup, and for whatever element we have in the second subgroup, those elements are going to commute with each other. So we could take A1 times A2, and that would be the same thing as A2 times A1. And then for the final condition that would need to be satisfied, we're saying that for all elements in the big group, G, there exists some element in the first subgroup and some element in the second subgroup, such that any element from G can be written as a product of those two elements. And I wanted to also write just some notation that we'll see throughout the video series. I'll probably mention it again too, but one way of writing this condition, because this is kind of a long condition to write, going from here to here, right? But if it's true that any element of G can be written as some element of H1 times some element of H2, then we can write that more generally by just saying that by just replacing the elements with the corresponding groups. What this is telling us is that pick any element of G, that is going to equal some element of H1 and some element of H2. So simply this equation right here is a very compact way of describing this overall condition. They mean the exact same thing. And often, and we'll see this more later in some of the upcoming videos further down the line, but this is a notation that can be useful, and I just want to make sure we know what that means. Okay. So let's go through showing ultimately this direct product theorem. Now, in the last example, we used the idea that we could look at the elements of a group to determine if two groups were isomorphic or not. But let's also, and that's very useful, like looking at the rules associated with pieces of a chessboard. But let's also just remember what it means definition-wise, purely from the definition, what it means for a group to be isomorphic to another group. And two groups are going to be isomorphic if there exists an isomorphism between them. So then what's an isomorphism? Well, an isomorphism is a homomorphism that is bijective. So another way of showing, what we're doing is we're showing different ways here that we can establish that groups are isomorphic. And what we're going to do to show that G is isomorphic to H1 cross H2 is by showing that a bijective homomorphism exists between these two groups. So we need to check off both properties. First thing we're going to do is just to define what that isomorphism is. So let's say that we have a function f, because again, an isomorphism is just a function, right, that has properties. And the domain of f is going to go from H1 cross H2, and it's going to map to G. And specifically what we're going to have is that if we have f, and if the input is a Cartesian product, that means it's going to have two inputs in it, right? The input is an ordered pair, I should say, where the first element, maybe A1, comes from H1, and the second input, A2, comes from H2. So this ordered pair is an element of the domain, and it needs to spit out just some element of the codomain, G. So not an ordered pair, but just a single element, because we have a single set for our codomain. And we're going to call this A1 times A2. So this is the function that we're going to look at. And what we would like to do is to show that it is an isomorphism. It is a bijective homomorphism. Usually, it really doesn't matter, but usually the first thing that you want to do or that at least I have grown to typically do, is that an isomorphism needs to first be a homomorphism. And usually showing that something is a homomorphism is a relatively straightforward check. So I'm going to do that first down here, just to show that something's a homomorphism. Let's quickly remind ourselves what it means to be a homomorphism. Basically, any function between groups that satisfies f of x times y equals f of x times f of y. This is a function that preserves the group structure. This is what it means to be a homomorphism. So we need to show that this is true for this specific function f right here. So let's do that. Let's first take a look at the left-hand side, f of a product of two elements in the domain. So when f is a product of two elements in the domain, one element in the domain might be this element, a1 comma a2. And then it is in a product with another element from the domain, which maybe I'll call b1 comma b2. And same idea, right? b1 is an element of h1, b2 is an element of h2. And if we were to, and we would like to show that we eventually get to this right-hand side right here. So let's do that. We know that if we were to first just evaluate the input to this function, we have f of a product of two things. Let's first take the product of those two things. According to how the direct product was defined, we know the binary operation with the direct product, right? So we know that if we were to take a1, a2 times b1, b2, we are going to get a single ordered pair as the output of this product right here, where that single ordered pair output is going to be a1, b1, comma a2, b2, like this. This just came from the definition of the binary operation defined when we were talking about direct products of groups. Right? We're talking the binary operation associated with this group. Okay, so now we have f acting on a single ordered pair. let's actually do that on how it's defined. We see right here, this is how f was specifically defined. When f acts on an ordered pair, the output is simply the product of the elements in the ordered pair. So let's go through that. The output of this is just going to be the product of the elements in this ordered pair. In other words, this element, a1, b1, times this element, a2, b2. Right? This is good. Now, what we can do is what's kind of nice about this theorem is that since these conditions need to hold 1, 2, and 3, we can use these as tools to help us along the way throughout the proof. These need to be true in order for the overall statement to be true. So we can use these as helpful tools. And one of the tools is the second condition right here. Whatever element we have from the first subgroup, whatever element we have from the second subgroup, they need to commute. A1, A2 equals A2, A1. What we have right here is a product of elements from the various subgroups. But specifically right here, we see that B1 and A2 are next to each other. B1 is from H1, A2 is from H2. So because these are from different subgroups, they can commute with each other. So we can rewrite this as A1, A2, B1, B2. And notice just for a second too that the subgroups H1 and H2 that we have right here, they don't need to be commutative by themselves. They don't need to be abelian groups. That's what it means to be commutative, right? We don't need A1 and B1 to commute, or we don't need A2 and B2 to commute. The only thing that we really needed was B1 and A2 to commute. We needed commutativity across different subgroups, even if commutativity isn't satisfied within the individual subgroups by themselves. Okay, so just kind of a neat thing to keep in mind. These groups don't have to be abelian. But regardless, we have this result right here, and now it's just a matter of recognizing what this is equal to. If we say that, if we were to focus just on A1, A2 and just B1, B2 by putting parentheses around them, that's like looking at the output of this function. What is A1 times A2? Well, A1 times A2 is simply f acting on the ordered pair A1, comma A2. So this thing right here is really f acting on A1, A2. And this right here is f acting on the ordered pair B1, B2. And that's what we were trying to show, right? We were trying to show that f of x times y equals f of x times f of y. Therefore, we've shown the first part that f, this function that we defined right here, it's at least a homomorphism. And that's the first step. What I'm going to do now is I am going to erase the board, because that's the first part in showing something's an isomorphism, right? It needs to be a homomorphism, but also needs to be bijective. And if something's bijective, it needs to be both injective and surjective. So we're going to erase the board, maybe leave this definition up right here, and then we're going to show that it's a bijective function, and that will prove the theorem. Okay, so now to show that it is bijective, right? So we need to show both that it's injective and surjective. And it doesn't matter which order we do it in, but we'll start with the injective condition. And if you remember, this was from a couple videos back now, but we showed that a function was injective. Maybe let me just write this so we have this in our heads. But a function f is injective. So f is injective if and only if the kernel of f is simply the identity element. So the kernel of f is simply the identity element. And that might not have seemed so important at the time, but we established this because this is an equivalent condition to show that a function is injective. So rather than showing that f is injective through the standard definition, this is a completely equivalent way of doing so. So let's do that. So we want to show now that the kernel of this function is simply the identity element. That is the only element that can be input into this function and spit out the corresponding same identity element. Okay. So how do we do that? Well, let's say that we have an element in the kernel of f. And if we have an element in the kernel of f, that tells us that F acting on whatever that element is. And let's just be general for now. Let's call that just some ordered pair. This is an element, and if it's in the kernel, it's going to map to the identity in the codomain. It's going to map to E. All right. Now let's just apply what this function is according to its definition. F of the ordered pair is just the product. So another way of saying this is that the product A1 times A2 is equal to E. Now, since we know that groups have inverse elements, we can multiply both sides of this equation on the right by A2 inverse and get that A1, A2, A2 inverse equals E times A2 inverse, like this. A2 and A2 inverse cancel. E times A2 inverse is just A2 inverse. So this tells us that A1 equals A2 inverse. All right. Just some standard manipulation of group elements right there. Hopefully those make sense. Now, what we can do is we can say, all right, we have this condition so far. If A1 comma A2 is an element of the kernel, that's what we said right here, then that implies that A1 is equal to the inverse of A2. Let's dig a little bit deeper here. Now, A1 was the first element, or the first input in the ordered pair, so it belongs to H1. So let's write that out. We know that A1 is an element of H1. A2 is an element of H2. But since H2 is a subgroup, that means that it is inherently a group. Any element in H2 has to have an inverse that's in H2. So what I'm trying to say is that if A2 is in H2, then its inverse is in H2. So we know that A2 inverse is in H2. Okay? So this is what we have so far. And if A1 is in H1, A2 inverse is in H2, and we know that they happen to be the same element, that's what we showed right here, that A1 is equal to A2 inverse, then what we can say, what we can say is that whatever we call this element, whether we call it A1, which is the same thing, it's equal to A2 inverse, whether we call it A1, A2 inverse, we know that if it's in this group and it's in this group, another way of saying that is that it is an element of the intersection of the two groups, H1 and H2. If it's in this one and it's in this one, regardless of what we call it, it has to be in both, right? Okay, now what we can do is we can be very convenient and use our condition number 1 right here. We haven't used that one yet. And this necessarily needs to be true for the theorem to work. The first condition is that this intersection needs to equal the set that only has the identity element in it. So what we are saying is that this set, another way of saying H1 and H2, is simply the set containing the identity element. I'm close to making the brace, right? Close enough, right? So let's see what this says. What this is saying is that A1 equals A2 inverse, which is in the set of one element, the identity element, right? So what does that mean? That means that A1 is the identity, right? Because it's in there, and A2 also has to be, A2 inverse has to be the identity, right? Now, what do we know about identities? And maybe I'm going too slow here, but I'd rather be too thorough than not thorough enough. What do we know about identity elements? We know that E times E, identity times the identity, is the identity. This is just a property of any group that we have, regardless of the group. So if we call the first input A2 inverse, and the second the inverse of A2 inverse, so A2 inverse inverse, we are going to get the identity. And what is the inverse of A2 inverse? That's just A2, right? The inverse of the inverse gets us back to the original element. So another way of saying this is that A2 inverse times A2 is the identity. But if A2 inverse inherently was the identity, what we said right here, replace that with this and we get that A2 is the identity. I said a lot of words there. The main thing you needed to take away from that is that A1 is the identity and A2 is the identity. If you got that, you're good. And here's why. The reason why is because that tells us a statement about our original assumption right here. We said if A1 comma A2 belong to the kernel, which was this condition, what we have just shown is that the only way this is true is if we have f of A1 being the identity, A2 being the identity, mapping to the kernel. And if this is the only way this is possible, this ordered pair is the only element of the kernel. The only element of the kernel of f is the identity. What we have just shown is that going from here all the way down to here is simply just showing that this is true, therefore the function's injective. Okay? That was the first part. Now we have to show that it is surjective. And before you say, oh my god, this is going to take even longer, don't worry because we haven't used condition 3 yet, but condition 3 basically says that the function is surjective. Let's remind ourselves what it means for a function to be surjective. It says that every element in the codomain gets mapped to by at least one element in the domain. What do we have right here? Every element in G, the codomain, gets mapped to, or is equal to A1 times A2. And another way of saying A1 times A2 is f of A1 acting on A2. So maybe another way of just writing condition 3, and maybe let me erase the bottom of the board so I have room to write this. Again, this is to show that it is surjective. For all elements in G, for all elements in the codomain, we have A equals A1, A2. Another way of writing A1, A2 is this condition right here. F of A1, A2. So what we are saying is that every element of the codomain gets mapped to by some element of the domain. By definition, this is what it means. Condition 3 tells us what it means for a function to be surjective. Therefore, f is injective, surjective, and a homomorphism. So therefore, it is an isomorphism. And since an isomorphism exists between G and H1 cross H2, they have to be isomorphic to each other, thus proving the direct product theorem. A lot of steps, but hopefully individually, these steps make sense. I'm going to call it for this video before saying one more thing, but this will be quick too. You'll see that you might want to prove that one group is isomorphic to a direct product of groups. What you can do is you can just check off each of these 3 conditions, and if each of these 3 conditions are satisfied, that's a way of showing that this is true. This is a third way of showing that groups are isomorphic, that these types of groups are isomorphic between each other, if these conditions check out. Now I'm done. Thanks so much for watching, and we are going to be moving on to a new section after this, so I'm very excited, and I hope you guys are as well. So yeah, thanks so much, and I will see you guys in the next one.